record. And I will share as usual. If you have questions, please don't be shy about asking. Let's see if we can do that. Screen mirror. All right, so we're going to talk about the cross products. Before we do that, I just want to say something about determinants. So this is something that some of you may have seen before, some of you may have not been exposed to it. So here's the basic idea. We're going to have to talk about matrices and determinants. So a matrix is the singular of matrices, and a matrix is just a rectangular array of numbers. Get the chat here. Okay. And a determinant is a function that takes a matrix, a rectangular array of numbers, and gives you one number out, a scalar out. Okay, so we've got a couple of definitions here. So here's an example of a matrix.
Sorry, Professor, can you call back to the previous slide?
Sure. Do you have a question, or you just need to come?
Oh, no, I just needed to do a screenshot of those.
I just have a question.
Yes.
What does the word say after takes and determinant?
Oh, sorry. S-Q-U-A-R-E, square.
Oh, thank you.
Sorry, my using a stylus on a screen is not good for neatness for me. It's hard as a left-hander. Okay, everyone have what they need here? Everyone good? Okay, so here's an example of a matrix. 1, 2, 3, 4. That's a square matrix because it has the same number of rows, right? The top row is 1, 2, the bottom row is 3, 4. And the number of columns, right? Leftmost column is 1, 3. Rightmost column is entries 2, 4. So that's an example of a square matrix. Here's another example of a square matrix. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now I have 3 rows and 3 columns. Okay, and the determinant right? So here's the determinant function. It's being applied to the matrix with entries A, B, C, D. So notice that's a Square matrix, same number of rows and columns, right? 2 of each. And by definition, this takes the value A times D minus B times C. Right, so you multiply the diagonals and then you subtract those two products. Okay. And you can write down sort of a definition for how to compute the determinant of a general square matrix, no matter how big it is, sort of as a formula. But that formula is kind of complicated to interpret. So there's an iterative way to think about computing determinants of larger square matrices. Damn, I can't spell. Okay, so please let me know if anyone needs more time to copy something from this page. All right. Is there anyone who needs more time? Okay, so no response, so I will go forward here. So the idea is, so let's take this matrix. The 3x3 matrix, 3 rows, 3 columns. If I want the determinant of that matrix, so here's some notation first. So instead of writing out the name of the function determinant, so please mute yourself unless you're asking a question, because there's noise sort of gets it's into the Zoom session. So we have the function determinant. We could also write that by replacing the brackets that we use to represent a matrix by just vertical brackets like this. And what we do is there's an associated sign matrix. So it's a checkerboard pattern of plus minus signs. Okay. And you could think of taking any row or any column of your determinant. I'm going to take the top row here. I'm going to copy the entries of that row with the signs that come from this matrix. So there's a +1, there's a -2, and there's a +3. And then for each of these numbers in that row we picked, we're going to multiply by a smaller 2x2 determinant. So we're going to take, for the entry 1 here, we cross out the row the 1 appears in. So cross out the top row, cross out the column the 1 appears in, that leftmost column, and we're left with a smaller square matrix. Okay, so we take the determinant of that so-called minor, the smaller matrix. And then we do that for each of the entries in this row. So let me maybe change the color here. So for the 2, right, the 2, we get rid of the top row and the middle column. We're left with these entries. And then for the 3, I don't know, let's do red. For the 3, get rid of the first row, the rightmost column. And the point of doing this is that we've our 3 by 3 determinant, now we can compute as a number of 2 by 2 determinants. Okay, and in the same way, if we had to compute the determinants of a 10 by 10 matrix, we could pick a row or column of that matrix and reduce to the problem of 10 9 by 9 determinants. For each of the 9 by 9s, we could reduce to the problem of 8 by 8 determinants and so forth. For our purposes in Math243, we just need to know about 3 by 3 determinants. So once you get down to here, we have our rule for how to compute determinants of 2 by 2s. Okay, and then we finish the calculation and we get a numerical answer. Okay, now, why are determinants important? Okay, so before I move on, get what you need from this page. Let me know if anyone needs more time. Is everyone good? Okay, so why do we care about determinants? Why do determinants come into play? Well, you may have encountered something called Cramers Rule. So this is a way of solving linear systems of equations. So let me just pause for a second. Has anyone heard of Cramers Rule? Yeah. So some no's, some yeses. So you don't really need to know Cramers Rule, but the point of Cramers Rule is that it, if you have the right type of linear system, you can look at certain matrices that are related to the coefficients in that linear system. And you can write down the solution in terms of determinants of those coefficient matrices. Right, essentially it gives you a formula. Okay, so Cramer's rule comes into play because it really gives you a formula for solving certain linear systems. And let's look at a problem that you might need to work on with certain vectors. So given two vectors, A, B, where A is equal to A1, A2, A3, B is equal to B1, B2, B3. You may want to compute or to find a vector which is perpendicular to both of those. And let me just use X, Y, Z as the terms there. All right, so based on what we learned last week, how could we express the fact that this vector C has to be perpendicular to the vector A, for instance? So there's something, say that again?
We know it's perpendicular if the dot product is, if the dot product is 0.
Excellent, exactly. So I want A dotted with C is equal to 0. And essentially that means that A1 times X, oops, what's happening here? Plus A2 times Y, plus A3 times Z has got to be 0. And we also want this vector C to be perpendicular to B. So, oops. So we can say that B dot C is equal to 0. So B1X plus B2Y plus B3Z is equal to 0. So that's a set of two linear equations in three unknowns. Okay, the unknowns being X, Y, and Z. So if you've solved linear systems before, you might expect that with fewer equations than unknowns, there should be infinitely many solutions. And in fact, that's the case. There are many, many solutions here. Geometrically, think about the following. You've got two vectors, A and B. Okay. And with those two vectors, you can define a plane. You can determine a plane. And now you want a vector which is perpendicular to both of those. That means you want a vector that's perpendicular to the plane determined by A and B. But notice that if you've got some solution to this, any non-zero scalar multiple of your basic vector is also a solution. So think about this first equation here. If you've got an X, Y, and Z that makes this true, then if you multiply through by 2 in this equation, you can see 2x, 2y, 2z will also make the equation satisfied. So there's lots of solutions here. Because it is a linear system, you might expect that Cramers rule in some form is gonna be involved with your solution. And in fact, you could do this formally. I'm not going to go through all of that, but you can find the general solution to this set of two equations here. There's going to be infinitely many solutions there. And if you impose a couple of extra conditions, you can pick out a unique solution. So doing that, okay, so So what we want to do is we want to fix the orientation of the solution in reference to those two vectors A and B. And we want to fix the length of the solution. So notice if I've got my two input vectors, A and B, say, I could have lots of vectors pointing this way, or I could have vectors pointing this way. So I'm going to pick one of these, and I'm going to pick the orientation by imposing the right-hand rule, okay? And I'm going to say that with these requirements, I'm going to define the cross products of the vectors A and B. And it's called the cross product because we used the sort of time symbol there to represent the cross product. This is a vector, of course, and it acts on vectors with three components. So unlike the dot product, the cross product is defined only for, excuse me, vectors with three components. And we're going to introduce sort of a funny determinant here. Okay, this is not really a determinant because I've got two different types of entries here. I've got the vectors I hat, j hat, and k hat, as well as the numbers A1, A2, A3, B1, B2, B3, which are the components of my vectors A and B. But determinants are involved sort of in the background in some sense, because we're solving a linear system. With these extra requirements, we can use this particular determinant as a device to help us remember actually how to write down the solution of that system. So we're going to take the I hat with a plus sign, the j hat with a minus sign, the k hat with a plus sign. And then we're going to make a smaller 2x2 determinant. The minor for the I hat is A2, A3, B2, B3. The minor for the j hat, get rid of the top row middle column. A1, B1, A3, come on, A3, B3. And then with the k hat, we've got A1, A2, B1, B2. Okay, and then we compute these smaller 2x2 determinants, and finally we're left with a vector. Okay, so that is the definition of the cross product. Right, so let me just pause for a second, make sure you've got what you need from this page down. Does anyone need more time here? Are we good? Okay, so what's going on with the cross product? Well, there's lots of properties of the cross product. That you need to be aware of. So number one, A cross B is orthogonal. All right, remember that means perpendicular. To A and B. Right, so remember the cross product lets us compute a vector which is perpendicular to two given vectors. The orientation of A cross B is determined by the right-hand rule. Okay, so remember we've seen the right-hand rule in the context of right-handed coordinate systems. The positive z-axis has a certain relationship to the positive x and the positive y-axis. If you start with your fingers pointing along the positive x-axis, curl towards the positive y-axis, your thumb is going to be pointing in the direction of the positive z-axis. So similarly here, if we point our fingers in the direction of the vector A, curl the fingers towards the vector B, your thumb is going to point in the direction of the cross product of A and B. And notice that if you reverse these two vectors, there's a relationship reversing those two vectors actually reverses the orientation. Okay, and this is a consequence of the right-hand rule. If I start with my fingers pointed along the vector B and curl towards A, my thumb is going to point in exactly the opposite direction as if I start with my fingers pointed towards A and curl towards B. Okay, so that's an important property of the cross product. The magnitude of the cross product, by definition, is going to be related to the magnitudes of the two input vectors. You take the length of the first vector times the length of the second vector, and then multiply by the sine of the angle between the vectors. Okay, and that theta is the same theta that we saw with the dot product. Remember, the dot product says A dot B is equal to the length of A times the length of B times cosine theta. Those are the same thetas. So the dot product of two vectors is related to the cosine of the angle between them. The magnitude or the length of the cross product of two vectors is related to the sine of the angle between them. Okay. And let's see here. So does anyone need more time on this page?
I have a question.
Sure, go ahead.
So the dot product is absolute value of A times absolute value of B times cosine theta. Right?
So this is the same symbol as absolute value, but this is really the magnitude of the vector, the length of the vector.
Oh, okay, I see. Thank you.
So remember that the line underneath the symbol means that you're dealing with a vector, and when we have a vector and we write this, we mean the length of the vector, it's not really the absolute value. Right. Any more questions? Right, so if the vector v has three components, v1, v2, v3, remember we have this really from the Pythagorean formula or the Pythagorean theorem. So you might remember that the dot product of two vectors gives you an easy way of determining whether the vectors are perpendicular. The cross product gives you an easy way of determining whether two vectors are parallel. Okay, so if theta happens to be 0 or pi, or in degrees, 0 degrees or 180 degrees, the sign is 0. So the cross product of two vectors that point in exactly the same direction or exactly the opposite direction has to vanish. So another important property. Two vectors are parallel. Oh, I should be more careful here. Two non-zero vectors, A, B, are parallel if and only if A cross B is equal to the 0 vector. Okay, and if I want to leave this as a vector, I can leave it as a 0 vector. The only vector whose length is 0 is the 0 vector. Okay. So what's the geometry? Well, let's draw two vectors here. So that could be A. B, say. So let's imagine that I wanted to find the area of this parallelogram. A and B. Well, these were at right angles. That would be easy because it's, in that case, we'd just have a rectangle. It's not that much harder for parallelogram. We can actually think about cutting off and then moving that piece over to get a rectangle. And it's clear in that case that the area is just the length of this vector B times whatever this distance is from the top to the bottom of the parallelogram. But let's think about that. What is this distance? Well, we've got a triangle, right? And we've got a right triangle. So it turns out that this altitude here, right, is related to the sine of this angle. So the sine of theta here would be the length that we're looking for divided by the length of the hypotenuse. So if that's question mark, sine of theta is equal to question mark divided by the length of our vector A. So the thing we're looking for is really the length of A times sine of theta. Okay, notice that's exactly what we picked our formula for the cross product to guarantee. So the length of the cross product of two vectors gives you the area of the parallelogram determined by the two vectors. Okay, so that bit of geometry is built into the definition of the cross product. And we'll actually see that come back a number of times as we go further through the course. So it's very important that you make note of this and remember this. Okay, this is an important property. I'll give you a few seconds to copy whatever you might need from here. Ask any questions if you need to before we go on, please. Okay, so is everyone ready? Anyone need more time? All right, so there's something that's pretty closely related to this parallelogram area idea. So if we have a parallelogram, let me forget about vectors here for a second. If we've got a parallelogram and we cut that into two pieces using a diagonal, these two areas are the same. Two parts of equal area. Okay, so if we put our vectors back in there and think about this, so we might be interested in the parallelogram. We also might be interested in the triangle. Right, so the triangle is just half the area of the parallelogram, so just have to remember that little bit of geometry. Okay, so let me ask you guys,
Sorry, could you come back for a second?
sure.
Thank you.
Okay, anyone else need more time? Are we good? Okay. So I'm going to ask you guys to compute I hat cross j hat. So I'll get you started. So remember, we put I, J, K in our top row. We put the entries of the first vector in the middle row. We put the entries of the second vector in the bottom row. And then we use our formula based on determinants. So what's the result going to be here?
Oh, wait, I have a question. Where did you get 1, 0, 0 and 0, 1, 0 from?
What is I hat? It's exactly this vector. That's a unit vector in the positive x direction.
Oh, thank you.
Okay, j hat is the vector 0, 1, 0. It's a unit vector in the positive y direction. So remember, unit means length 1. And k hat is the vector 0, 0, 1. That's a unit vector in the positive z direction. All right, so what was our formula for computing the cross product? We take down I hat with a plus sign, j hat with a minus sign, k hat with a plus sign. I hat comes in with a 2 by 2 determinant. The entries are, 0, 0, 1, 0. Okay, does everyone see where that determinant is coming from? Okay. And then with the j hat, we've got 1 0 0 0. With the k hat, we have 1 0 0 1. All right, so I see a variety of answers for the result here. Let's, before we go any further, is everyone clear on that step of getting it down to 2x2 determinants? Is that good? Good. All right, so 2x2 determinant, we get 0 minus 0. 2x2 determinant, 1 times 0 is 0, 0 times 0 is 0. With the k hat, we've got 1 times 1 is 1, minus 0 times 0 is 0. So this result is going to have 0 I hat plus 0 j hat plus 1 k hat, or in other words, 0 0 1. So the answer is the unit vector k. Is everyone clear on where that's coming from?
Yeah, I just have a question.
Sure, go ahead, Andrew.
Does that mean if you cross, like, let's say we crossed I and K, would the result of that be J? And if you cross J and K, the result of that would be I?
Well,
Or do those come to different results? It's not like a property.
so in fact, there's something that's called a cyclic relationship between these two, between those unit vectors. So I cross J happens to be K. I cross K happens to be minus J. And these are not that hard to work out. So let's do I cross K and just see what we get here. Come on. So I hat with a plus, 0 0 0 1. J hat with a minus. We have 1 0 0 1. K hat comes in with a plus. So that's 0 I hat minus J hat plus 0 K hat, or minus J, or 0 minus 1 0. Okay, so remember, you can use the right-hand rule to work these out. I hat, J hat, and K hat are mutually orthogonal to each other. So if we cross I and J, you know it's going to be something times K. And the result's going to be a unit vector if you cross unit vectors like this that are perpendicular to each other. Basically, the only thing you have to worry about is figuring out the sign, SIGN, plus or minus, and that you can work out from the right-hand rule. So there's a cyclic relationship, which you sometimes see, right? So think of a circle with these guys. I cross J is equal to K. J cross K is equal to I. Remember, if you reverse these, you pick up a minus sign. So you could do I cross J, J cross K, K cross I, and then reverse all the reverse the orders, and you can figure out your answer using this little circle.
All right, thank you.
Okay. So I don't think I'm going to be able to cover everything in 12.4 in full detail, but On page 819 of your book, there's a box with the properties of the cross product. Okay, make sure you memorize these. And more important, understand where these are coming from. Okay, so some of these we've talked about already. I just want to point out that there's distributive laws. I can distribute the cross product over a sum of vectors like this. The order matters, remember, with the cross product. Right, so I can't just willy-nilly replace A cross B here by B cross A. If I switch the order, I have to remember to introduce the minus sign. There is something called the scalar triple product. And notice that you really don't need the parentheses here, because if you try to take the dot product of A and B, you would get a scalar. You can't cross a vector and a scalar. So this only makes sense if you do the cross product of B and C first, and then take the dot product of that result with the first vector A. It turns out, however, that if you swap the cross product and the dot product, the answers happen to be the same, strangely enough. Okay, and that's something you could work out with some tedious algebra. It's actually not that mysterious. It turns out that the scalar triple product of three vectors, either one of these two, is really the 3×3 determinant. Of the entries of the three vectors that we're dealing with. And because of that, there's actually a direct geometrical interpretation of the scalar triple product. So notice here, A dotted with B cross C, that's the scalar triple product of those three vectors. That's a number which could be positive or negative or zero. If I take the absolute value of that number, what I actually get is the volume of the rectangular parallelepiped determined by the three vectors A, B, and C. Okay, and again, this is something that we'll see later in the course, and you might see this in other courses as well, because this is a geometrical result, which is important in a number of contexts. Okay, so I think that's about all the time I have for today. One more mention, applications of the cross product. Torque in physics is the cross product of two certain vectors. When you talk about torque measured in foot-pounds, you're really, or the appropriate metric unit there, you're really talking about the length of the torque vector. Other places where the cross product comes into play in the governing equations of fluid mechanics, electricity, and magnetism. and actually lots of other places. So that's where we have to stop for today. Thank you for your attention. And I hope that everyone has a good day. Okay, I can hang around for a little while if people have questions. So otherwise, you're free to go. Remember, I have office hours a little bit later today.
All right, see you, bro.
Okay,
Thank
have a
you.
good day, everyone.
I have a question, Professor.
Sure, go ahead.
When do we have quizzes?
I think I'm going to start at the end of this week with the quizzes. So there were some adjustments made to the schedule, which just came out very recently from the registrar, and I knew those were coming. I didn't want to schedule anything until I knew exactly what
Oh, okay.
we would be
No,
missing.
I was just, I didn't want to, because I'm usually late for lectures because I have practice. So that would be really helpful. If
So Julia, I'm going to do the quizzes outside of class, so I will post them on Canvas.
Oh,
You will have sort of a window to work on them, so don't worry about being on time to class. Okay.
okay. Thank you.
So don't stress. Okay.
Okay. Thank you. Have a nice day.
You too. Okay, did anyone else have questions? What the heck is going on with my glasses?